All right. Good morning. Any questions or comments? Okay, I want to start talking about Berry curvature of the Bloch bands. Exactly what we did so far, but for the Bloch bands, and see what geometrical structure of Bloch bands demonstrate. So the Hamiltonian we have in mind is, like, let me remind you something like this. We consider H 1 over 2m P plus E over C A square plus V of R, and V of R is periodic. And in this setting we introduce magnetic translations. For example, we show that H commutes with some decorated translational operator TA, and this TA1 and TA2 also commute. If A1 and A2, like the placket spanned by A1 and A2, has integer quantum flux. In that case, we could use the Bloch theorem, psi and k of R. So I will not write vectors again because it's too much clutter. So it's going to be e to the I kr u and k of R. And Bloch theorem says we can write it like, okay, there are different versions, but let me use this one. And in that case, this T decorated translation TA u and k of R is going to be equal to u and k of R. So that's the content of the Bloch theorem. Now we can unpack this T tilde and see, remind ourselves this generalized Bloch condition. So this T, let me just copy this. So this thing is equal to e to the I some phi a of R, and then translate u n k R plus a, and this should be equal to u n k of R. So that's what we call generalized Bloch condition. Now if you plug this in here, so what we are going to find is standard thing, like we just operate either e to the ikr or e to the on u, and after e to the ikr did its job, we just cancel the things. Then what we are going to find is something like that: 1 over 2m p plus, let me just write vectors here to emphasize the structure, plus e over c a, okay, this is R dependent, squared, plus V of R, this entire thing acting on only Bloch functions uk of R, and they give you en k un k of R. And from here we immediately see this entire object can be considered like some h of k, and k are adiabatic parameters.
There is also R dependence.
Yes, there is also R dependence, but the slowly varying external parameter, right, in the formalism is not R. R is like dynamical coordinate, if you want. K is, we are imagining, it's like we can slowly change it, and then this will generate all the geometrical effects. So once you have this, I think we can also think about u and k being k dependent. In that case, we can just define, let me just write Berry connection I u and k del k u and k. So this is how we define the Berry connection, and the corresponding Berry curvature Bn of k is going to be del k curl of A and this can be defined for each band. So each band has its own curvature. So by acting this derivative to here, right? So this is like a cross product which is anti-symmetric, and derivative can act on here or there. But from the cross product there will be like epsilon ijk. Epsilon ijk is anti-symmetric. Second derivative here is going to be symmetric, so they will cancel each other. By doing the calculation, what we are going to find is like something like that. Let me write it. Del k u n k. So this is cross product. It is not the position x times del k u n k. And if we are in 2D, we can also unpack the content of this thing, and we are going to find, okay, this is in 2D Brillouin zone. This is I del, let me write del x for del kx, and same for ky. So this is going to be, right, the cross product, k can have x and y components, and something crossed in terms of x and y is going to be perpendicular to x and y, and this is going to have only z bn z component. Then this is going to be del x u n k del y u n k minus exactly the same thing, x and y replaced. So this is y, this is x. Okay, so that's the Berry curvature of the Bloch band in 2D, and that's the Berry connection. Since we are talking about the geometry of the Bloch band, we also need to emphasize the geometry of the Brillouin zone. So let me start with 1D. In 1D, so k, there's only one vector, and it is minus pi over a to pi over a. And we can think about this like a segment, but the ends are identified. But this is identical with like a circle, right? So this is the topology of the Brillouin zone in 1D. In 2D, we have exactly the same thing. There's like two of these. This is kx and ky. And Brillouin zone is going to be like a square. So you identify this edge with this edge, and this edge with this edge. What is this shape? If I connect these two ends, what kind of geometrical object do I get? Imagine you just roll it, connect to here, and you just roll it, connect here to here. What's that? Torus, right? So this is like something like that. So this is T2 torus. And in 3 dimension you have 3 torus, and in a D dimension you have D-dimensional torus. Now I want to derive semi-classical motion, semi-classical equation of motion, and I want to show you something like a. So, what is the observable consequence of this curvature? Right? We are speaking about like a curvature, and if we have this curvature, how can we see it as we observe? For that, let me write it like semi-classical equation of motion and anomalous velocity. So the key idea is like this The reason I'm trying to write this curvy, because in a little bit I'm also going to consider magnetic field. I want to distinguish magnetic field from the Berry curvature. But so far our understanding is like B n of k is acting like magnetic field. And we know magnetic field is going to generate like a transverse velocity, and it is responsible for Hall effect. So, and transverse velocity. And the question is, can we also obtain transverse velocity from this Berry curvature? And answer is yes, and I'm going to try to show you that. But previously, if you remember, we calculated the nk. Let me write it like this: dr dt psi nk was equal to. We like did a lot of if you want, you can write this like p over m2. So, and what we found was unk del hk del k unk. So I think use Hellman-Feynman theorem to get to this, and after that we showed it's equal to 1 over h bar del enk del k. So we have to drive exactly the same thing in the presence of a Berry curvature and see if it's the same or different, and the result is going to be different. So this was for Bn was 0, but now we need to take Bn not equal to 0. So there are like a couple of ways to do this, and all of them are unfortunately sticky. And if you look at Gordon Young, he also tries it in 3 ways. And I didn't like any of these, so I tried my own way. My own way also has like some problems, but like when we drive this, right, this semi-classical equation of motions, you know, you have to take them with a grain of salt. If you want to drive them from a macroscopic calculation, it's very tedious, right? And typically what we say is like, that's the emergent, right? You put the electrons in like a lattice, they do what they do, and this wave packet emerges. And if you want, that's the fundamental thing. Deriving them from like a macroscopic principle may not be needed if you look like that. So for that, I want to define generalized velocities. Like now I go back to parameters. So I want to consider this h of r. R is not position again. It could be any adiabatically changing parameter in the Hamiltonian. And r, I will take r1, r2, dot, dot, dot. And I want to calculate this object, this generalized velocity v is equal to psi in some eigenstate del mu h psi n. And here again, del mu is short for del r mu. Okay. So what we said, this adiabatically changing Hamiltonian has instantaneous eigenstates. So if you want, we wrote it like this: h of rt, n of rt was equal to en of rt, n of rt. And we said if you, as you evolve in R parameter space, this new state, this psi n of t, is going to evolve into this state up to a phase, right? Some theta of t. And this phase had 2 contributions. Theta of t was equal to gamma n of t. This was the geometrical phase, and the second one is 1 over h bar from 0 to t dt prime en r of t prime. And this one is the usual Schrödinger phase, right? The dynamical phase. So what we need to do is like we put this psi n to these generalized velocities and calculate the expectation value, but it is a little bit tedious. I mean, you can also do that, but I think it just becomes a little bit untractable, at least for a classroom calculation. So what I will do is, because this psi n and n of r, they are like adiabatically connected, I will use n to calculate the expectation value. And then it is reasonable to anticipate the same expectation value should survive for n, but I will leave it as an exercise, like put this extra phase and do exactly the same calculation. There will be many terms, but they all cancel. So keep your faith and do the calculation, but to keep it short, I want to do it with n. So I want to let v mu be equal to, so this n. Now, okay, we are adults, n is r dependent. Okay, I don't need to write it. We know it, just keep in mind, because it's going to clutter the page. It's harder to follow the calculations if you write too many symbols. So this is n, del mu h n. So this thing is the thing I want to calculate. So use n rather than psi n for brevity, and you can do the longer calculation for yourself if you have the appetite. And the Schrödinger equation I h bar del t n is equal to h n. So this is again r dependent, but I'm not going to write it, but these are instantaneous eigenstates. So this is going to be E n, again r dependent, n. Okay. Now I want to hit on this. You see, we are doing something really strange. That's the thing about the time dependent Hamiltonians. You are writing both time dependent Schrödinger equation, and you are also thinking about time independent Schrödinger equation, and then you just go back and forth. It could be a little confusing or disorienting, but that's the magic of this thing. So I want to hit del mu on both sides of this equation. So this is I h bar. Okay, let me just write it and then hit with del mu. So this I want to compactify like this. So this is del t, because now I know this is acting on here, and I add one more mu, and this thing can act on Hamiltonian n or the state del mu n. Now hit from the left hand side with n. In that case, what I'll find is, okay, let me just copy. So this thing is n, and this thing is going to be, and again this n is also r dependent. Let me just repeat, just in case you forget. This is like that. Now we have like two things. First, so this piece, I can use Schrödinger equation I h bar del t n is equal to h n. Take the Hermitian conjugate of both sides, minus I h bar del t n is going to be n h, and Hamiltonian is Hermitian. And this side is also going to require some work. This one. So let me start with again I h bar del t n is equal to h n, and I hit with bra from both sides. So this is going to be n. So this is going to be n, and we know this is just E of n, just the energy. And now I hit with del mu. Okay, let me write it on the other side. Del mu and what we need to do, del mu, this del mu can act on here or there. So let me just erase this. Del mu n del t n plus I h bar n del mu del t n is equal to, so I'll also act on here, del mu epsilon of n. So this thing kind of looks like, not at the moment, but to me it looks like barrier connection. At least I can work with this. So this I want to modify a little bit. So this one is yes. So that's the object we are trying to, oh, I see. And this one, okay, here, okay, I think exactly, that's the point. So this I h bar, so this object, then from this calculation is going to be equal to del mu epsilon of n minus this thing. That's exactly what we are looking. Yes, that's correct. Then, so I will put everything in back to here. We are trying to manipulate this line. So then let me just write one by one. So this thing. So this thing. So now I have this term is equal to this thing n del mu h n, and this thing is minus, actually let me just bring the minus from here, actually let me write it minus I h bar del t n del mu n, right? So I take this and this one. And the object I'm interested in is here, right? This is the generalized velocity. So v of mu is equal to this object. And this one, so this is the definition, and this one is equal to, so del mu epsilon of n, so this thing is taken care. Let me push it a little bit. And minus this thing minus this thing. Good. Okay. So now this thing is normal group velocity we derived before, group velocity. Right, there is nothing surprising about this. This is the new contribution. So this one is, let me write it like V nu A. So this is anomalous. So that's the one I want to work a little bit more. So this thing is, let me just copy this entire thing. Hopefully you already have a sense that, you know, this kind of looks like very curvature, but we need to finish the calculation to make sure we get that. Actually, let me just erase h bar. So this thing, I want to, okay, there is like time derivative, but these n's are parameter dependent, right? So what I want to do is del t n, I'm going to write it like this, sum over sum mu del, my parameters are r, del r del t mu. Okay, this is new sum. So this is new sum. This is new in derivative, and this is n. So I'll substitute it here. So this is going to be equal to
New or what?
so the new, right? R has like components. I have to do this change of variable for each component. So x del t del xn plus del y del t del yn, and for the same for z. So then this is going to be I sum over new del r new del t times, let me just copy this, because the only change is going to be this t is going to be new and this t is going to be new. Good, and this is exactly what we had in mind. This thing, color blue, so this one is what we called omega mu nu, so-called Berry curvature in our earlier calculation. Now, so the velocity has like a normal component and a normal component in this abstract parameter space. Now I want to come back to crystals. For crystals, so we need to replace R with K, H with this H of K, and N here is going to be changed with, okay, let me write them next to each other, and we'll change with un of k, the Bloch functions. In that case, this velocity is, let me use little r to show the velocity, dr dt is equal to, so there is this usual component, but in the case of like a k, if you remember, there was this 1 over h bar del en of k del k. Actually, let me write it like a little bit in different notation. So this is del k en of k minus, so there is I have dr dt, but this dr dt is going to be replaced with k here, so it is going to be dk dt, and this thing, let me write and check if that's the case. This thing times, you can see this is mu, new mu, right? There's some like index gymnastic we need to take care, but this is going to be Berry curvature and of end band. Okay. So now let's check this. So I want to look at the components of this thing and see if it has exactly this structure. So this is going to be, so I want to look at the new component of this. I want to look at new component. So this is going to be epsilon mu nu rho dk nu over dt and b and mu nu, and this is going to be rho, but b n of rho is going to be equal to del k cross. So this is Berry connection, a rho component, and it is going to be epsilon, let me rho eta chi. So this is del eta a chi. So now I substitute it here. There is like one epsilon coming from here, another epsilon coming from here. I have this thing and I have this thing. And a chi, let's also unpack a chi. A chi is going to be u and k del chi. There's also additional I because of this definition, del chi u and chi. Okay. And this is the standard. I think everybody knows this. So this thing, right? You can just cycle and bring like rho and rho together. What will happen is del mu eta delta nu chi minus exactly the same thing. You just change the indices. Mu chi and nu rho. I think everybody knows this, right? It's standard thing for this entire symmetric tensor. So this is mu ta x. Okay. And so this thing, okay, here this thing is anti-symmetric, and there is like a derivative acting on this entire thing, and derivative can act on here or can act on the entire thing. But if it's acting on entire thing, there's like a derivative del eta del chi, which is symmetric, and you are multiplying it with something anti-symmetric, it's going to drop out. Then the only way this derivative can act is on this part, so let's also write that. Because of this symmetry property, the only thing that can happen here is this. Right, you see it almost looks like this, but we have to do the one last punch with this thing. So this is going to be I dk mu dt. So now I want to write this thing twice. This, so let me open up some space, minus, so first one minus the second one, and now I'm going to take care of indices. So eta is mu and chi is nu. Here eta is mu and here chi is nu. And if you look at term by term, this one, oh, here also we have summation convention, right? So here summation. So all of these are written with the summation convention. So this one didn't have summation convention. You are mu nu minus nu mu, and I have k mu nu minus, okay, this is minus nu mu. Okay, exactly the same thing. So same as above. Good. Okay, now let me just write the results and like generalize it and see what they actually mean. So we have velocity dr. So these are like semi-classical equations of motion with curvature, or like with band curvature. When I say band curvature, I don't mean trivial curvature. It's like this higher Berry curvature. dr dt is equal to 1 over h bar del k epsilon n of k. This is the usual contribution we had previously. Now we have this new contribution, dk dt cross b n of k. And this looks like a lot like Lorentz force, right? And we can also write dk dt. So dk dt, let me write it here, dk dt. I think I need to have like an h bar here. So h bar times dk dt is going to be gradient, right? So exactly like this gradient, but it is in the real space of some potential u of r. So this is Newton's law, right? H bar k is P, dP dt is the force. And there's also Lorentz force, E over C, dr dt cross B of R. So this is like electromagnetic fields in the real space. This is the Berry phase. So this, let me push them aside. So this B is curl in K space of this Berry connection. So this B is curl in real space of vector potential. So this A comes from, so this A and I, U, and K. Let me write the other notation. Del K, U, N, K. Where this A is not physical, right? We just use whatever vector potential works as long as it satisfies this condition. That's fine. So this one is scalar potential, and this one, you see, like it's really ridiculous if you think about it. There's a quantum mechanics coming from here. There is like geometrical effect coming from here. There's classical Lorentz force coming from here, and you just like put all these different things together, and it seems to be working. So this is coming from solution of Schrödinger equation, and these are the Bloch bands. That's why it's called semi-classical, right? It has both quantum content and classical content. Any questions? So let me finish with the one last observation to consider the symmetries of this equation that tells us a little bit about what to expect and when to expect. First, okay, once we have these equations, we can consider their symmetries, but I want to start with the symmetries of classical, okay, let's start with classical equation of motion, like Newton plus Lorentz. So what we have is like F is equal to m times A, and it is equal to Q E plus Q V cross B. So I think everybody knows this. And this is equal to, so this A is equal to D square R dt. So I want to consider what happens to this thing in the presence of symmetries, and there are two special symmetries we need to consider. One is time reversal. Under time reversal, okay, let me just write this equation again. So in the case of time reversal, okay, this is dt squared. T goes to minus t, r goes to r. So this thing is same as before. Q doesn't change. Under time reversal, how does E change? So E goes to the electric field. For example, think about Gauss's law. Does it change under time reversal? So E goes to E, so this doesn't change. So V goes to minus V. What about B goes to, what's that? Minus B, right? Then under time reversal, there are like two minuses. This didn't change. I also want to consider inversion. In the case of inversion, R goes to minus R. So let's write this equation again. If R goes to minus R and there's T, there's like a minus here. So there's like a minus here. How about electric field? E goes to, think about Gauss's law, minus, right? E goes to minus E. V goes to minus V, and B goes to B under inversion. But there's like an overall minus. You can see the equation of motion in both cases did not change. So, and that's what should happen, right? Same equations of motion under TR and inversion. Now I want to play exactly the same game but for these equations, so let's copy. I want to consider both time reversal and inversion separately. Let's copy to save some time. So now first time reversal, so this is TR. T goes to minus T, so there's like a minus. K goes to, T goes to minus T. K goes to, under time reversal, like crystal momentum, minus, right? It's like momentum, so there will be an additional minus here. Epsilon n, so if K minus goes minus, but spectrum is almost always symmetric, except very subtle, very specialized systems. This is always the case. So there's like minus K goes to minus K, T goes to T. This is still plus, and B goes to minus B. So this is going to be plus, right? And there is like here I need to put minus K here. So there is like, so one minus here, another minus. I think let me just erase this. One minus comes from here, another minus comes from here, and for B I will write it like this, and we still don't know how B behaves under time reversal. In a little bit I'll decide that. So there is no minus, so this sign we are going to determine in a little bit. So this one is still plus, K goes to minus K, T goes to minus T. This one is still plus. So there is like one additional minus here, but B also goes to minus. So this equation does not change. So no change. But for this equation not to change too, we require this Bn of minus K. If it is equal to minus of itself, then the equation of motion is the same. Is that clear? So we require this. So this is one. And now I want to do the same thing with inversion. R goes to minus R. So there is like a derivative. R goes to minus R. K goes to minus K. So there will be a minus here. And epsilon n of minus K is again epsilon n of K. So I won't change anything here. So K goes to minus K. Let's put it here. So this is minus K. There's like a minus here. And it seems like this minus is going to make this one plus. Whereas here I have like a minus. There's like a plus. B doesn't change under inversion. There's like a plus. So this equation, you can see the overall equation picks up a minus sign. But this equation, it seems like, needs to pick up a minus sign only if Bn of minus K is equal to Bn of K, right? There's already a minus here. I don't want any more minuses. Now the last thing I want to say, I will finish it here. So if both TR and inversion exists, then we have this thing from inversion and this thing from time reversal. It's going to be 0 because what we are going to see is this thing from one and this thing is from the other. But if you combine this, what does it mean?
The parameter for the first equation is plus, right? And on the right hand side.
Right hand side.
First equation, right? First.
This one.
No.
So this one.
The right hand side.
So this one is minus.
The inside of the
Oh yes, inside, yes. I think I messed it up. Yes, that's correct. Yes, I need to, because that's what the conclusion was. That if you put minus here, it's going to be like that. Okay, now it is done. So B of minus k in the presence of both time reversal and inversion is going to be equal to, because of inversion it is this, right? This is because of inversion. And now I use this line, but this is going to be minus b n of k. This is because of, so this is inversion, this is time reversal. Now I compare this line with this line. What did I do?
So the middle one is plus key, that is in parentheses.
Oh, this one is plus. Yes, yeah, this one is plus, right? Yeah, yes. Okay. Now I got it. So this is minus k because of inversion. This is plus. Now this entire thing is now because of time reversal is equal to this. Okay, now I compare not that but this. These two are going to give me b n of k is equal to minus b n of k. That means what? It's exactly the same thing. If something is equal to minus of itself, that means b n is, okay, let me also write k is equal to 0. And the messages, and that's the last thing, you need to break either TR or inversion to have non-zero curvature. Good. Any questions? Okay. Thank you.